It is now time to get a little bit deeper into valence bond theory and try to explain why this theory exists and what we would use it for, or what types of things it describes. And we mentioned before in the first little introduction to valence bond theory that valence bond theory says that a bond results from the overlap of orbitals. And as people looked at hydrogen and thought about wave functions and the physics behind electrons acting as waves, and when they start to overlap with each other in constructive and destructive interference, they started to have some really good ideas about how new orbitals could form from old orbitals and how the bonds can result from the interaction of orbitals and all this stuff. And so it was fairly attractive. Although when they started to think about the geometry of molecules, they ended up with a little problem. Because since the p atomic orbitals are 90 degrees from each other, if you attached atoms to these atomic orbitals, the bond angle there would be 90 degrees from each other also. So let me show with a quick picture what I mean by that. That if you have a p orbital along the y-axis, the py, and you have a p orbital along the x-axis, the px, and you bring in a couple of hydrogens, the hydrogen 1s orbital could overlap with the px, and that would attach whatever atom this is. Let's say it was a oxygen. So we're just trying to envision what water might look like. And you have a hydrogen come in and attach to this p orbital, and a hydrogen with its 1s orbital attached to this p orbital, and now your hydrogen-oxygen-hydrogen bond angle would be 90 degrees. And if you know about water, the real bond angle is about 104.5 degrees, and you could get the SN orbital involved, and it just seemed too fudgy to not have a whole bunch of 90 degree angles if overlap of orbitals was causing bonds. So since the orbitals exist at 90 degrees from each other, the bonds should exist at 90 degrees from each other. And thus chemists had to do something if they wanted to save this theory. So one way to look at this is we can replace the normal orbitals, as I call normal orbitals, these wave functions, and the set of wave functions describes the electron density around an atom, but you could replace that with new orbitals that equally describe the electron density of an atom, but with the correct geometry for bonding and minimized electron repulsions in the molecule. So it's always hard to describe in some sense how a set of atomic orbitals represents the electron density if you're not going to go through and do all the math and solve for the wave functions and everything. But there are different sets of wave functions that achieve the same goal. So again, the best analogy I could come up with after thinking about this a whole lot of times is if you wanted to build a square from parts, you could have square parts, right? So 4 little squares can be assembled to be a big square. So again, if your sum of your electron density was shaped like a square, your little pieces of electron density might be little squares, and that would make sense, right? That'd be one good way to build a square. But you could also build a square with triangles. So you could have 4 triangles and build a square. And so you wouldn't really have a reason to use squares or triangles if your only goal was to build a square. But if one of the other shapes in nature was big triangle, right, then you'd need the little triangles as building blocks. So there's a set of orbitals that would summarize the electron density in a free atom, and which of those orbitals we consider in making molecules will depend somewhat on what the molecule looks like. is sort of my best analogy for this idea of we take our normal orbitals that we think of, the s and the p, and we can replace them with new orbitals that equally describe the electron density, but they have better geometric features for building molecules. And there's different ways to do that. And so this is one of the things that's funny is there's different sets of orbitals, different sets of wave functions that can be used. So our normal way of thinking about this is we could have the 2s and the 2p orbitals, right? And so in an energy diagram, we might have 2s and 2p as being our valence orbitals, and that's where the valence electrons would be. In a sketch, we'd have the spherical s orbital, and we'd have these three figure 8 shaped p orbitals that are all perpendicular to each other. So that's what the normal orbitals look like. And now we could replace these. So I think of like going to the orbital store and giving up our s and 2 of the p's, right, the s and 2 of the p's. So we're going to do sp2 hybridization. So we're going to take the s and the 2p orbitals from the normal atomic orbitals and replace those. Mathematically, we'll be adding these using linear algebra, but again, that's really complicated. But the result of trading in those orbitals for 3 equivalent new orbitals is we get these 3 sp2 orbitals that are at the same energy. We have the p orbital we didn't use that will still be there, right? So the hybridized sp2 orbitals, which result from the combining of an s and 2 p's. Then we have a leftover unhybridized p orbital, and now the sketch of these guys is that the sp2 orbitals form a perfect triangle. So if you knew that your atom was going to be involved in a molecule with 3 things attached, then the way to minimize repulsions would be to use the sp2 orbitals to get the perfect triangular shape. And then the p orbital, and this is always really hard to draw for me, but the p orbital that would be left over would be perpendicular to the plane of this triangle. So I could try to draw a lobe coming forward and a lobe going back. The textbooks have much better drawings than I could draw, but perpendicular to this sp2 triangular plane would be the perpendicular p orbital that's unhybridized. And so for valence bond theory, if you want to form a molecule with the right shape and geometry, you need a new set of atomic orbitals to deal with that's got the right geometry for the molecule you're shooting for. If your electron domain geometry is trigonal planar, because you have 3 electron domains, then you would have to use sp2 hybrid orbitals to make that triangle, and so you do sp2 hybridization to get the result there. And then there's some terminology that I just sort of walked through as I was bringing in a new set of hybrid orbitals to replace the traditional atomic orbitals. But when an atom has 4 electron domains attached to it, then it's going to use the sp3 hybrid orbitals to form the bonds. So 4 electron domains, we need 4 orbitals to get involved. We'll need the s in all 3 of the p's. We'll trade the s in all 3 of the p's in to get 4 new shiny hybrid orbitals, which will be ready to form bonds or accommodate lone pairs of electrons. When an atom needs to accommodate 3 electron domains, it uses the sp2 hybrid orbitals. The bond formed between hybrid orbitals and a non-central atom is going to be called a sigma bond, sigma, And if the central atom has sp or sp2 hybridization, then it also has one or more unhybridized p orbitals that can form a different type of bond. So if you have sp hybrid orbitals, you've used the s and one of the p orbitals. Remember, you have an s and three p's, so if you just use an s and a p, you have two p's left over. If you use sp2 hybridization, you've used two of the three p's, and you have an unhybridized p orbital that's there. And these unhybridized p orbitals are going to form multiple bonds by overlapping side by side. The side-by-side overlap of p orbitals is going to form something called pi, or pi bonds. So this is some of the terminology, and we'll get a little more depth into this as we go, but the purpose of the hybrid orbitals is going to be to form single bonds or to hold lone pairs, and then the unhybridized p orbitals are going to be free to form multiple bonds. And we'll get into what those orbital interactions look like and some of the molecules that you can form using hybrid orbitals in future videos.